All right, well, it's a crazy math nerd here, and let's see, I think we're in part 4. We are in part 4 of this discussion of going backwards from the derivative. And so I told you in the last 2 videos, get ready because the chain rule is coming to town. So here we are, and so remember, what we're doing is we're going to be given the result of the chain rule, and we're going to be asked, who do you take the derivative of and get this result? So why don't we do like we did with the power rule? Why don't we really analyze what we do when we do the chain rule and look at the original problem versus the derivative and see what things are there and not there and so forth. So we're just going to do some derivatives so that we're going to actually go forward so we can go backwards. So let me get a fun pen here. I want a fun color. I feel purple today. There you go. All right, so we're just going to take the derivative and then analyze this. So let me tell you I'm taking the derivative. I'm going to leave the 6 alone just for emphasis. And let me do a big bracket here. Okay, so here's my big bracket. Oh, I didn't want that. I wanted purple. Oh, there's my purple pen. All right, so I know I'm having a hard time getting my pens going, aren't I? So there's my big bracket. And I'm going to do 5 times the parentheses. Leave the parentheses alone, right? Reduce the power by 1. And then I'm going to take the derivative of the inside, which is 6x squared, plus 0, right? If this is your inside, if you take the derivative of that, you get 6x squared, and then the derivative of that is 0. So that is my entire derivative. So some things to note. If 6 is in the original problem, it's also in the chain part, right? That's 6. This constant. The inside is in the chain part and in the original problem. Notice the powers are different, right? You went up by a power. And notice that this part, the chain itself, is not there at all. Oh, I forgot to add C, didn't I? No, I didn't. I'm going the wrong way, crazy person. So this chain part does not exist in the original problem because it is a result of the chain. So whatever is the result of the derivative of the inside is not in the original problem. Let's keep that in mind. Let's keep that in mind. It's not in the original problem. Okay, got to make a line there. All right, so now let's take the derivative of this trig function. Well, in order to take the derivative of a trig function, you have to know that the derivative of cosine is negative sine. You leave the theta or the angle alone. I always call that guy theta. I always call him theta because he represents the angle, the cosine of the angle. So you leave theta alone, and then you take the derivative of the inside. So is this in the original? No. But it has to be in the derivative because it's the result of the chain. Okay? So when you're doing a power, you do your power rule. When you're doing trig derivatives, you do the pattern of who is the derivative of that, and then you take the derivative of theta. All right, let's look at an E situation. So dy dx is equal to, you leave the 9 alone, a constant stays there. The derivative of e to the power is e to the power no matter what, and then you take the derivative of the power. So notice that this part is not in the original problem because it is the result of the chain, but it has to be in this answer. The result of the power, the derivative of the power has to be in the derivative as part of that chain rule, right? And then last but not least, we have a natural log situation. Love it, love it, love natural log. We're not scared of logs at all. The 7 will remain there because it's just a constant. And we're going to do 1 over whatever that is times the derivative of whatever that is, which is negative 2. So notice that the inside of this derivative is in the bottom. That's why I said earlier that if you see a function in the bottom, there's a really high probability you're dealing with natural log. The 7's in there, but look, the -2 is not in the original problem, but has to be there as a result of the chain. All right, so now that we've got this thinking, let's go backwards. So now I'm going to pose you with a problem. Here is the derivative. Where did it come from? Well, I can clearly see that the derivative of x cubed is sitting right there. That is the chain part of the derivative. The whole thing, because the derivative of this inside is 3x squared. It is there. That means that this thing to the fourth is what is the outside part of the function. You know how we do the outside and then take the derivative of the inside? This is a result of taking the derivative of the outside. And this is the derivative of the inside. Okay, so in order to find where it came from, the outside part is to a power. So I am going to do the anti-power rule. I'm going to take that inside, and I'm not going to change it at all, and I'm going to add a power and divide by that power. What happens to the derivative of the inside as we back up into the original problem? Will it be there? No, because this is the answer to the derivative. This part is the answer to the derivative. And so that is the result of the chain rule. That will not be in the original problem. So we just add C. Got to add that constant. So let's say that you're going right now, I do not believe her. She is lying to me. Well, here's the cool thing. Let's come over here and prove me right or wrong right now. So let's take the derivative of my answer. And if I did, I'd get 5. Leave that alone, right? Take a power of 1 away. There's already a 5 down there. And then the derivative of the constant 0. Now notice what happened. Oh, and then times the derivative of the inside would be 3x squared. So I just did the power rule around this. I'm just confirming if I take the derivative of y, is it what I started with? So notice your 5's would cancel, and you do end up with your original problem right there. Okay? So it's all about recognizing the pattern that it is the chain rule and figuring out how to go backwards with it. The thing that really freaks some people out is what happens to the 3x squared. Because it's not in my answer, like that's my answer, it's not in my solution of that. And so it's not in there because it was part of the chain. So when I back up, it's not going to be in my original problem. Right? So this was a power situation, so I did the anti-power rule to go backwards. So when I get to a problem that involves E, I have to think to myself, what do you know about derivatives of e to the power? Well, I know that if you take the derivative of e to the power, you get e to the power no matter what, and then you must apply the chain rule. So I do know that this e to the 4x comes from taking the derivative of e to the 4x. I know that for sure. But the thing is, I'm thinking to myself, well, if I took, let me think about it, if I took the derivative of e to the 4x, remember that's that weird notation that lets you say you're taking the derivative, then that should be e to the 4x times 4. There should be that derivative of the power there. And that 4 is not there. I don't see, there should be a 4 right there, and I don't see it. So ask yourself, what could have been in the original problem so that if you had the 4 and you wrote it down, it would cancel it? What could be in the original problem that would cancel that chain of the 4? So there must have been something there. So what do you multiply by 4 to get 1? And that's 1/4. And don't forget my constants. So let's say you don't believe me, because I bet you don't. So if I'm saying that if you integrate this, you get this, I'm saying that is y, right? That's what I'm saying. I'm telling you the solution to this is y. So if I say y equals 1/4 e to the 4x, let's take plus c, let's take that derivative, shall we? So if I do that, y prime equals, leave the 1/4 alone, and if you take the derivative of e to the power, you get e to the power times the derivative of the power plus 0. And notice that the 4 there and the 1/4 there would cancel, and that's why we don't have a number right there, because there had to be a 1/4 in the original, and you do end up with your original problem of e to the 4x. So if you're missing part of what you know should be in the chain, and that part you are missing is a number, then in the original there had to be something in the problem that is canceling that number that you know should be there. So let's look at some problems that look kind of similar to each other but are really different. So we're going to start with, and I'm going to go back to red. I like writing in red. It's a pretty color. I really wish I had some pink, but I don't think I have pink. Do I have pink? Let's try pink. Pink, purple, purple it is. All right, this is a pink purple. So when I see this, you know how I said if you see something in the bottom, you're really thinking that could be natural log, right? So the first thing I'm going to think about is, see this constant up here? This has nothing to do with the derivative of the bottom at all. It's just some random number. So in my answer, I'm going to put a 3 because it's there in the problem. It's going to probably be there in the original. It's there in my answer, right? It's probably going to be there in my problem because it's just hanging out there. It has nothing to do with 4 minus x at all. And let's just say I think this is the answer. Let's just say I think that this is the answer. Okay, let's say I'm saying that's equal. So this is the antiderivative, and excuse me, this is the derivative. Sorry, this part is the derivative, and we're saying this is the antiderivative. So like this is y prime, and we're saying this is y. That's y. So here's the thing. If that is truly the answer, then I should be able to take the derivative, and it should give me the problem I start with. So let's try that. So if I take the derivative of this, I get 3 times 1 over 4 minus x times the derivative of 4 minus x, which is -1. Oh no. No. That's not, okay, that's not it. Because that should be my problem, my integrand. That should be my integrand if I do it right. And notice I'm missing that -1 in here. There's not a negative there. So in my original problem, there should have been a negative in here. I should have put a negative in here because the derivative of the inside is -1. It is not in my problem, so it's not in what they gave me, right, my integrand. So it must be in my original problem. So when I do the derivative, it would cancel. So notice now if I had a -3 right there, this negative would cancel with that, not cancel, but they would make a positive, and I would end up with my original statement. So if you're missing a negative or a number, then you have to account for that. There must be going something on in the original problem for it not to show up in what they're asking you to find the antiderivative of. Okay, so I'm going to go through my thinking one more time with you because that was kind of quick. Sorry about that. So here's how I think about this. Okay, so I say the 3 has nothing to do with this problem. Well, it has nothing to do with the derivative. Has nothing to do with the derivative of 4 minus x at all. So I'm just going to write it down. It must be in the original problem hanging out. This 4 minus x is on the bottom, so I'm very, very thinking this is natural log because that's what natural log does. Remember, this is somebody's y prime. That's what that is. That's somebody's derivative. And when you take the derivative of natural log, it throws it on the bottom. But the derivative of this thing on the bottom is -1, and I do not have a negative in this answer. So I'm going to have to put in a negative into the original problem because it must counter the one when I actually do take the derivative and do the chain rule. So natural log of, and another little ditty that you're going to have to learn how to do is put the natural log of whatever that is, that quantity must be put in absolute values because we do have a restriction on natural log in that the quantities, the natural log of that quantity cannot be negative. So we're going to start putting those in absolute value bars. So here is the answer. I feel good about this. And again, if you don't feel good about it, come on, I gotta pick a pen, I guess. If you don't feel good about it, let's do this. Let's take the derivative of this, and if we don't get our original problem, then we're wrong. So here we go. So this is like my y. That's my, and I'm thinking that, it's not equal to it, but I'm thinking, come on, thinking cloud. I'm having a hard time with my pens right now. That is y. That's y. So if I take the derivative of this, I get -3, 1 over 4 minus x times -1. And is that the original problem I started with? See how your negatives are going to cancel, and you end up with 3 over 4 minus x. Yes. So what's so great, if you think you know what the antiderivative is, if you take its derivative, if you don't end up with a problem you started with, then you haven't done it correctly. Now this second, we're going to call this A, B, and C again, so we have some reference. That's A. We're going to call this B and call this C. So in B, this is a little different because the derivative of the bottom is 3x squared. And I do not have a 3x squared anywhere in this problem. That means at this time, I cannot integrate this. Let me say that again. If 4 minus x cubed is my, I think that that's the bottom, and I think that that is my my inside function. The derivative would be -3x squared. Now I could take care of the negative and the 3, but I can't just make up x's. You cannot just say, hey, I'm going to divide by, x squared, and that's going to take care of it. If you don't have the variable part of that inside's derivative, you cannot integrate that as far as you know. Okay? And another misconception is like this, the 4 minus x and the 4 minus x. This 4 minus x is under a radical, and so really I can think of this as 4 minus x to the -1/2. And that is not a natural log situation. That is a power situation. Okay? So if it's a power situation, the first thing I have to do is I have to think about, okay, this is the inside. The derivative of this inside should be here. And the derivative of the inside is negative. It is not here. There's no negative here to take care of that. So in the original problem, there must be, so when I do take the derivative, it'll cancel. So you have to take care of that to begin with. What am I missing? If I'm missing a negative, it must be the original problem, because that's what I'm kind of trying to find now. I'm trying to find that y. So then I'm going to add 1 to 1/2. If you add 1 to 1/2, that gives you +1/2. And if you divide by 1/2, well, we know that's bad notation, isn't it? Sorry about that. Didn't mean to move that so much. So I think that makes the 2 come up. So it's -2. Right? See how that 2 is going to pop up? The square root of, because that's what to the 1/2 means, 4 minus x plus c. Don't forget your constant. Okay. So a lot of times, the reason I wanted to show you this one, a lot of times when people see something on the bottom that's raised to a power, they just say it's the natural log of that. You cannot do that. This cannot be raised to a power. It has to be to a power of 1 for it to be a natural log situation. And that means the answer is the natural log. All right, so here's some examples of problems that you can work. If you'd like to work these right now, go ahead and just stop the video and do the work. And when you hit play again, I'll be working them. Or if you just want to watch me work them, here we go. So here's example 1. And again, I'm just having pen problems today. I think I'm going to go with my rainbow because I love it, but I'm going to make it a little thinner. So remember what this integral means. The integral means, who do you take the derivative of and get sine? Well, you take the derivative of cosine and get sine. So I know that this is from cosine of 7t. Remember that theta will be the same. You don't touch it. But then I think to myself, the derivative of cosine is negative sine. And I don't see a negative there. So there must be a negative in the original problem. Also, if I took the derivative of this inside, there should be a 7 there, and there's not a 7 there. So in the original problem, I must have a 1/7. Add your constant, and you're done. If you don't believe me, take the derivative of this. If you don't get your original problem, like seriously, like this is the integral of this, the antiderivative is this. And if you want to prove it, then take the derivative of this. If you don't get your original problem, then I'm wrong. I mean, you can check it if you don't like it, okay? In example 2, there's this random 9 that has nothing to do with the inside. If that were 6, that'd be great, because that would actually be the inside that I need, but it's not. It's a random 9. So if this random 9 is here and has nothing to do with the derivative of the inside, then I just write it as part of my problem, because it must have been there in the beginning. You know how we just carry those constants through. So then I ask myself, where does secant tangent come from? Who do you take the derivative of and get secant tangent? And that's secant. And you got to remember that we got to keep that theta, whatever it is. And then you say, but there should be a 6 in this answer. There should be a 6, right? It should be secant 6 theta, tangent 6 theta times 6. But I don't see a 6. Do you see a 6? So in the original problem, there must be a 1/6 that would counter that. Add C. Now I know that that 9/6, I know that reduces, and so I could say that that's 3/2 secant of 6 theta. Whoop, that theta is terrible looking, sorry about that. Plus C, I'm running out of room. I guess I can just scoot it over. And so I know I could do that. So if you don't believe me, sometimes just doing the derivative, you go, oh, that's why that happened. So let's say you don't believe me. Let me erase this. We'll just do this right here. Let's say you don't believe me. So I'm going to say that y, I'm having a hard time on my pens, that y is equal to 3/2 secant of 6 theta plus C. Let's say I said that. Then dy dx would equal, the 3/2 would stay there. And then you would say the derivative of secant is secant theta tangent theta times d theta. 2 goes into 6, right? The 2 and the 6, the 2 and the 6, right, would cancel, giving you 3. And 3 times 3 would be 9 secant 6 theta tangent 6 theta. Is that our original problem? Well, look, by golly, it was, so we're right. Okay? So you have to take things that have nothing to do with this, the derivative of the inside, just with you. And then if you're missing something that should be in the chain rule, you have to take that into account, that the reciprocal of that must be in the original problem in order to cancel it. Okay? I did want to show you this one right here, because this is a special pattern. This is the arc. Okay, so if you take the derivative of arc sine of x, you get 1 over the square root of 1 minus x squared. That is the derivative of arc sine. So this fits this pattern perfectly. Now the reason I'm saying this is because if you really wrote this out, this would be 9x squared, and the derivative of 9x squared is not in the top, right? So this is, or it's not anywhere. It's not in the problem. So this is not a power thing. It fits a different pattern. So you need to be on the lookout that if you have things under the square root and that x is squared, you might be dealing with one of your patterns that's your arc functions. The other one is the derivative of arc tangent is 1 over 1 plus x squared. So if you're dealing with either of those, you need to be able to recognize those as a pattern, because, you know, I would normally look down here, like if somebody said, what's the integral of 1 over 1 plus x squared? I tell you, my first inkling is to go, is the derivative of the bottom and the top, because that would be natural log. And it's not, because I need a 2x for the derivative of the whole bottom to be there. And I don't have the x. I can take care of the 2 but not the x. And so I have to recognize that that is a direct pattern. So that is actually arctan. Oh, well, I didn't put an x there. Sorry. Arctan x plus c. So you do need to know that those two patterns because that'll throw you off. Okay, that's it for this one. I'll probably do another video with working some more examples for you. But it's just looking at patterns and taking care of what you're missing that should be in the pattern. All right, thanks so much. See you again. Bye. Math Nerd out.